In 2019, a Chinese rover made a discovery on the moon's far side that has scientists baffled. A mysterious, gel-like substance glinting in a crater, unlike anything in the lunar sample collection. Strange glass beads scattered across the surface containing elements that shouldn't be there, and volcanic evidence that challenges everything we thought we understood about the moon's geological death 3 billion years ago. China's Chang'e 4 mission was supposed to be a routine exploration of the far side. Instead, it opened up questions that are rewriting lunar science. What exactly did they find in those ancient craters? And why does it suggest the moon might be far more geologically active than we ever imagined? Let's break down the discoveries that are forcing us to reconsider everything we know about Earth's closest neighbor. There's a side of the moon you've never seen. Not from Earth, not with a telescope, not with your own eyes. For billions of years, one half of the moon has remained completely hidden from our planet, locked in place by gravitational forces we call tidal locking. We didn't see the far side of the moon until 1959, when a Soviet spacecraft flew past and sent back grainy black and white images. And what those images revealed was shocking. The far side looked nothing like the near side we've studied for millennia. No vast dark plains, no familiar lunar Maria. Instead, a surface absolutely covered in craters, scarred by billions of years of cosmic bombardment. It was like discovering that the moon had a secret face, one that told a completely different story. For decades, this mysterious far side remained largely unexplored. It's harder to reach, impossible to communicate with directly from Earth, and scientifically puzzling. But in 2019, China did something no nation had ever done before. They landed a rover on the far side of the moon, and what that rover found has left scientists struggling to explain. To understand what makes these discoveries so significant, you need to understand China's Chang'e program and why landing on the far side was such a monumental achievement. China started its lunar exploration program in the early 2000s, decades after the Apollo missions ended. While other nations moved on to other priorities, China methodically built a comprehensive lunar exploration capability. Chang'e 1 and 2 were orbital missions, mapping the moon's surface in unprecedented detail. Chang'e 3, launched in 2013, successfully landed on the near side with the U-2 rover, making China only the third nation to soft land on the moon. But Chang'e 4 was different. The mission target was the von Karman crater, a massive 186-kilometer-wide impact basin located within the even larger South Pole-Aitken basin on the far side. This is one of the oldest and deepest impact structures in the entire solar system. Landing there meant solving a problem no space agency had tackled before: communication. You can't send radio signals through 3,500 kilometers of solid rock. So China launched a relay satellite called Kuei-Chao, positioning it at a special point in space where it could see both Earth and the far side simultaneously. On January 3, 2019, Chang'e 4 touched down, and the U-2 rover rolled out onto terrain that no human-made machine had ever explored. For the first few months, U-2 conducted routine exploration. It analyzed soil composition, measured radiation levels, studied crater formations, standard lunar science. But then, on the mission's 8th lunar day, something caught the rover's attention. The driving team noticed an unusual reflection in one of the navigation camera images. There, in a small crater just meters away, was something that didn't look like normal lunar regolith. It was shiny, gel-like, completely different from the gray, powdery soil surrounding it. The team immediately halted the rover's planned route and redirected it to investigate. They positioned U-22's instruments directly over this mysterious substance and began a detailed analysis. What they found defied easy explanation. The material had an unusual color and luster, almost glass-like in appearance. Initial spectroscopy suggested it might be impact melt glass, formed when an asteroid strike melted lunar rock and it rapidly cooled. But the composition was strange. It contained minerals and elements in combinations that didn't match typical impact glass formations. Even more puzzling, this wasn't an isolated finding. As U-22 continued its journey across the von Karman crater floor, it discovered more anomalies: unusual glass beads, strangely colored regolith, rock fragments with composition suggesting volcanic activity far more recent than the moon's supposed geological death 3 billion years ago. Let's focus on that gel-like substance because it's the discovery that grabbed the most attention. The Chinese team was initially cautious about publishing their findings. They spent months analyzing the data, running simulations, consulting with international experts. When they finally published their results in 2019, they described it as impact melt breccia with an unusual color and luster. But here's what makes it so strange. Normal impact glass on the moon forms when an asteroid or comet slams into the surface at tens of thousands of kilometers per hour. The kinetic energy is so immense that rock literally vaporizes and melts. As this molten material cools rapidly in the vacuum of space, it forms glass. We've seen this countless times in lunar samples. The Apollo astronauts brought back impact glass. We understand the process. But this material was different in several key ways. First, its color. Most lunar impact glass is dark, often black or very dark brown, because lunar rock is inherently low in volatile elements and rich in iron. This substance had a greenish tint with unusual transparency. Second, the location. It was sitting on the surface in a relatively small crater, but spectroscopic analysis suggested it was relatively young in geological terms, possibly only tens of millions of years old instead of billions. Third, and most puzzling, was the elemental composition. The material contained higher concentrations of certain elements that shouldn't be enriched in impact melt. Some researchers have suggested it might not be impact glass at all, but rather a form of volcanic glass, which would indicate the moon had volcanic activity far more recently than we thought possible. Beyond the gel-like substance, U-22's journey across von Karman crater revealed another mystery. The crater itself tells a strange story. Von Karman crater is located inside the South Pole-Aitken basin, which is absolutely massive. We're talking about an impact structure roughly 2,500 kilometers in diameter and up to 13 kilometers deep. It's one of the largest confirmed impact structures in the entire solar system. When something that big hits a planetary body, it doesn't just create a hole. It excavates material from deep within the crust, possibly even the upper mantle. This gives scientists a rare window into the moon's interior composition, layers that are normally buried kilometers below the surface. Here's where it gets interesting. The rocks and soil that U-22 analyzed showed an unexpected composition. Scientists were expecting to find primarily anorthosite, the light-colored rock that makes up most of the lunar highlands and the moon's original crust. Instead, they found significant amounts of olivine and low-calcium pyroxene. These minerals are typical of the lunar mantle, not the crust. This discovery suggests that the impact that created the South Pole-Aitken basin was so violent, so deep, that it punched through the entire lunar crust and exposed mantle material. We're essentially looking at the moon's interior, dragged up from depths that have never been sampled before. But there's a complication. Some of the mineral ratios don't quite match our models of what the lunar mantle should contain. Either our models are wrong, or the moon's internal structure is more complex than we've assumed. Now let's talk about the volcanic glass discoveries, because these might be the most paradigm-shifting findings of all. Among the samples U22 analyzed, scientists identified glass beads with a very specific composition. These weren't impact glass. The chemical signature was completely different. These were volcanic glass spherules, tiny beads formed when volcanic material is ejected into the vacuum and cools while airborne, creating perfect little glass spheres. Here's why this matters. The conventional understanding of lunar geology says the moon's volcanic activity essentially died about 3 billion years ago. The moon is small, it cooled quickly, its interior solidified. Without plate tectonics or a large molten core like Earth's, there's no mechanism to drive continued volcanism. That's been the consensus for decades. But some of these glass beads tell a different story. Using radiometric dating techniques on the spectroscopic data, researchers have identified glass formations that appear to be significantly younger. We're talking about volcanic activity potentially as recent as 2 billion years ago. Some researchers have even suggested evidence for volcanism within the last 100 million years, though this remains highly controversial. If true, this completely rewrites our understanding of the moon's thermal evolution. It means the moon's interior stayed hot and geologically active for far longer than our models predicted. Perhaps there are heat sources we don't understand. Perhaps radioactive decay in the mantle continued at higher rates. Perhaps tidal heating from Earth played a larger role than we thought. The implications extend beyond lunar science. If we're wrong about the moon's geological timeline, a body we've studied for over 50 years, what else might we be wrong about regarding other planetary bodies? One of the biggest mysteries that Chang'e 4's discoveries highlight is this fundamental question. Why is the moon's far side so dramatically different from the near side? This isn't a subtle difference. It's stark. The near side, the face we see from Earth, is dominated by dark volcanic plains called maria. These are ancient lava flows that filled massive impact basins billions of years ago. They're smooth, relatively flat, and geologically younger than the surrounding highlands. The far side has almost no maria. It's dominated by ancient cratered highlands, some of the oldest terrain in the solar system. Scientists have debated this asymmetry for decades. One theory involves the moon's formation. The leading hypothesis is that the moon formed from debris after a Mars-sized object collided with early Earth. In this scenario, the moon initially had a magma ocean covering its surface. As this magma ocean cooled and solidified, heavier minerals sank while lighter minerals floated, forming the lunar crust. But here's where it gets complicated. The near-side crust ended up being thinner, around 30 to 40 kilometers thick. The far side crust is much thicker, potentially 60 to 80 kilometers in some regions. This thickness difference might explain the volcanic asymmetry. When large asteroids hit the moon, they created massive basins. On the near side, with its thinner crust, these impacts created fractures deep enough to allow magma from the mantle to flow up and fill the basins. On the far side, the thicker crust acted like armor. Even massive impacts couldn't fracture it deeply enough to allow magma to reach the surface. But this explanation has problems. Some near-side regions have thick crust and still show volcanism. Some far-side areas have thinner crust but no volcanic flows. The Chang'e 4 discoveries add another layer of complexity. If the far side had more recent volcanic activity than we thought, perhaps through different mechanisms, it suggests the near side versus far side story is more complicated than simple crustal thickness. So what do all these discoveries actually tell us about the Moon, and why does it matter? First, they fundamentally challenge our timeline of lunar geological activity. The idea of the Moon as a dead, geologically inert world for the past 3 billion years is looking increasingly questionable. If volcanic activity persisted much longer than we thought, it means the Moon retained internal heat through mechanisms we don't fully understand. This has implications for how we model the thermal evolution of all small, rocky bodies in the solar system. Second, the composition discoveries from the South Pole-Aitken Basin are giving us our first real look at the lunar mantle. Previous missions only scratched the surface, literally. The deepest Apollo drill cores went down about 3 meters. The Lunar missions reached similar depths, but the material U-22 is analyzing comes from potentially 50 kilometers or more below the original surface, excavated by one of the most violent impacts in solar system history. This mantle material is already revealing surprises. The mineral ratios don't perfectly match our models. There might be more water locked in the lunar interior than we suspected. Some researchers are even suggesting the possibility of a partially molten layer still existing deep within the Moon. Third, these findings are directly relevant to future lunar exploration and settlement. Understanding the Moon's resource distribution, its geological history, and the composition of different regions is crucial for planning sustainable lunar bases. If there's water ice in permanently shadowed craters, as we suspect, and if there are minerals and elements concentrated in specific geological formations, knowing where to look and what to look for becomes essential. Chang'e 4's discoveries are helping build that geological map. But perhaps most importantly, these findings remind us how much we still don't know. We've been studying the Moon for over half a century. We've sent dozens of missions. 12 humans have walked on its surface. And yet it still surprises us. It still reveals secrets that overturn decades of consensus. If the Moon, our closest celestial neighbor, can still hold these mysteries, imagine what we'll discover when we truly explore the rest of the solar system. Chang'e 4's discoveries have opened more questions than they've answered, and the next generation of lunar missions is gearing up to investigate further. China isn't stopping with Chang'e 4. Chang'e 5, which successfully returned samples from the near side in 2020, brought back the youngest volcanic rocks ever collected from the Moon, dating to just 2 billion years ago. This confirmed that lunar volcanism persisted far longer than the 3 billion year cutoff we once believed. Chang'e 6 is planned to return samples from the far side itself, potentially from the South Pole-Aitken Basin. If successful, it would be the first mission to bring far side material back to Earth for detailed laboratory analysis. This is crucial because remote spectroscopy can only tell us so much. Having actual samples that scientists can examine with the full range of laboratory instruments could definitively answer questions about the mysterious gel-like substance, the volcanic glass age, and the mantle composition. NASA is also planning to return to the Moon through the Artemis program. While Artemis focuses on the lunar South Pole, future missions will likely investigate the far side as well. The scientific community is particularly interested in placing seismometers on the far side to study moonquakes and probe the lunar interior. Understanding the Moon's internal structure through seismic data would help resolve questions about whether there's still a partially molten layer and how heat is distributed within the Moon. Europe, Russia, India, and private companies are all planning lunar missions over the next decade. Some will land in the South Pole-Aitken basin. Others will drill deeper into the surface than ever before. There's even discussion of a lunar far-side radio telescope, which would be shielded from Earth's radio noise and could observe the universe in frequencies impossible to study from Earth. The far side, once the hidden face we could only dream of exploring, is about to become one of the most scientifically active locations beyond Earth. Chang'e 4 landed on the far side expecting to study ancient dead geology. Instead, it found evidence that rewrites our understanding of how long rocky worlds stay active. The gel-like substance, the young volcanic glass, the mantle materials that don't match our models. Each discovery proves that even our closest neighbor, studied for over 50 years, still holds secrets we never imagined. And here's the thing, if the moon can still surprise us like this, what will we find when we truly explore the rest of the solar system? If you want to dive deeper into the mysteries of space exploration, subscribe to Orbital Atlas. We're just getting started uncovering what's really out there.